Hello, welcome back to Engineering Circuit Analysis. We're talking about op amps. Up until now, we've talked at great length about the basic principles of an op amp. We've talked about the inverting op amp configuration, which is really common, the summing amplifier configuration. Now we're going to talk about the non-inverting amplifier circuit. So in this case, we're going to talk about an op amp configuration where the output is not an inverted version of the input. Now, I could just give you the equations right now. I could write it down, tell you, here's what the circuit looks like, here's the gain equation, here's the output, here's the saturation region, and say, go, have fun. And most of you would probably do just fine, but I kind of see my job to sort of, explain what I've learned and kind of how these things come about so that you get a little bit deeper understanding than just using equations, like a monkey or something like that. So we're not trying to do that here, we're trying to understand. So before we actually get into actually giving you the punchline and deriving everything, I want to show you what I'm actually talking about by a non-inverting amplifier circuit. So we already talked about the concept of the inverting amplifier. Now, in all of the circuits that we've done, they've all been DC inputs, but still, I've been trying to kind of give you the idea as we've been going along that you can hook up alternating current. We haven't talked much about alternating current in this class yet, but you got to know where we're going. We're going to be having an alternating plus or minus current that might look like, let's say this. Let's draw a sinusoid or something like this, right? So the inverting amplifier, if you take this to the input, right, is going to give you an output signal on the output side that's going to be look exactly like the input, except every point that's positive is going to be mapped to be negative, and every point that's negative is going to be mapped to be positive. So if the input signal looks like this, the output signal is basically going to look something like this. Right? So you see every point that's positive becomes negative and every point that's negative becomes positive. So that's why in all of the circuits when I was DC sources, when I sent positive 1 volt in, you get a negative whatever volt out when we had the inverting configurations before. Or if I sent a negative half a milliamp in, you always got a positive value out because it was inverting it. Now you can also make the signal bigger or smaller. You can amplify it in the larger sense or in the smaller sense, but always in those inverting configurations, the sign of the output was always opposite of what the input was, just like I'm kind of drawing for you here. Now, in most applications, inverting an output like this is not a problem, right? But in some cases, maybe it is. Maybe you don't want an inverting version. Maybe you want to be able to amplify this thing, but not have it be inverted like this. So we're going to talk about how could you accomplish that. Now, you could accomplish it, you could hack it together by putting two inverting amplifier configurations in series with one another. So for instance, you could get an the kind of signal you're looking for if you're in the first stage of the amplifier, you put a signal in like this, and then the next stage in, right, what are you going to get? You're going to get, after the amplification of the first time, you're going to get something that looks like this. This is exactly what we've drawn on the board here. Well, you can take the output of this and feed it into yet another stage of the amplifier, which would take the previous stage here and invert it again. So you see, then you start with something like this and you end with something like this. So you could have amplification going on in the different stages, maybe make it a little bit bigger here and a little bit bigger yet here, and then you would have a signal that would look like this here and also like this. Now I'm not going to draw a detailed drawing of this, but between this guy, to make this happen, you would have an op amp that would look something like this. You would have some output like this. You would have, this is an inverting. I'm saying, how could we do this with inverting configuration is what I'm trying to say. Then we have something like this. We have an input resistance here and a voltage source like this, right? And then we have a feedback resistance, right? This is what we've been doing all the time. This is inverting amplifier configuration. That's going to take something with a positive input and give it a negative output if we tap it off of here. So this would be V naught, or V output, right? But then if we take this output, this V out here, and run it through another inverting op amp, which let's say we stick it in between these stages like this, so I'll change colors, and we'll draw this one in something crazy like pink, right? So we have exactly the same thing. We have another amplifier here. We have another output resistor. We call this one V out again. This would be plus minus, so it's an inverting configuration. This is tied straight to ground. And then here we have an input resistance. like this, and we're sending the signal in like this, and we also have a feedback resistance. Would you agree that this is also an inverting amplifier configuration, right? You have the inverting terminal where the input signal is driven in, you have a feedback resistance, source resistance, this is grounded, this is through an output. The only difference is, you see, basically you're going to take the output of this one, V out, and you'll connect it right over here to drive the second stage again. So you invert it here and you invert it again. That's how you could do all of this stuff with, in other words, if you really cared about the input signal not being out of phase or not being opposite signs of the input signal, you could hack it together by just putting two inverting amplifiers in series with one another and adjust the gains correctly, and you could do it all just fine. But then you have to have two stages. You have to have two op amps. So it increases the complexity of the circuit a little bit. Honestly, as far as a fast way to do it, that's probably the fastest way to do it because you have a lot of experience with making these inverting configurations. But in this lesson, we're going to talk about how to make a non-inverting, this is called a non-inverting amplifier because the input is not inverted with the output. We're going to learn how to make a non-inverting amplifier circuit without using two separate stages and connecting them together like this kind of hacked way to do it. We're going to do it with one op amp and a different configuration of resistors, and we're going to go through the proof to show you why the output is not an inverted version of the input, and it's going to have a different gain equation than the ones that we've used in the past for the inverting configuration. So I wanted to show you in a big picture, you know, how it would be done, and now we're going to go over here and show you, or how you could do it with inverting amplifiers. Now I want to go and show you how to build this thing with one op amp, and we call it the non-inverting amp, or the non-inverting op amp, right? So we have one amplifier, right, like this. And of course we have VCC, and we have negative VCC, as we always have. But other than that, it completely differs from what we've done before. So let me go ahead and draw this here. This is going to be plus, this is going to be minus, okay? And what we're going to have is over here, we're going to drive, or not we're going to drive, we're going to have a resistor here. We're going to tie that to ground. We're going to have a feedback resistor, okay? We're going to call this resistor R sub S. We're going to call this resistor R sub F because it's the feedback resistor. Now, the interesting thing here is, notice that in all of these other configurations, like down here, the inverting amplifier, we always drove the input signal into the inverting terminal. So that's why, you know, when you go through the math, you figure out the reason that we're getting an inverted output is because we drove the signal through the inverting terminal. Here, there's no source here. I'm not driving the input signal into the inverting terminal anymore. I'm actually going to drive it through the other terminal, through another resistor that I'm going to label here in a second for you, like this. So this is going to be plus or minus. We're going to call it V sub G. It's just the source voltage. I'm just calling it V sub G right now. And this is R sub G. All right, this is basically the what we call the non-inverting amplifier configuration. So let's label a few more things. We'll talk about it. And then what we're going to do is derive the gain equation that comes about from this configuration. And you'll see that it makes sense that it's non-inverting and so on, and you'll learn how to use it. So when you see something configured like this, you'll know how to handle a problem like this. First of all, the output is tapped right here. We call it V out. That's not terribly unusual. It's coming off the output like this. It could be a resistor that is across as well. All right. And then we're going to call this, remember, way back when we introduced op amps, we said the voltage here we called V1 and we called this one V2. The current going into this terminal was V1. The current going into this terminal was V2. So right now I'm just going to write this as V1 and write this as V2. And I'm basically going to put a little negative here. We'll do it like, do something like this. Put a plus here and a plus here to kind of remind you. Basically what I'm saying is that the voltage at this terminal of this op amp relative to ground is called positive V1, and the voltage here from this terminal to ground is called V2. And the way you can remember that, the convention anyway, is notice the V1 is a line here. The number 1 is a line. Well, that kind of goes with the inverting terminal. That's our convention. And 2 goes with the positive terminal. So this is basically what it is. So we have a resistor here, we have ground, we have a feedback resistor, and we have the resistor that comes after the source here. In this derivation, we're calling VG the source. Doesn't matter. It's going to be an actual voltage source in a real circuit. It might be 1 or 2 volts or whatever. This is going to be so many ohms, so many ohms, so many ohms, and so on. And when you drive a signal through this, and when you measure this on the outside, over here, you're going to be able to amplify it, amplify the signal, and you're also going to be able to see that the output is always, it's not inverted with the input. In other words, it's not going to be the negative sign of the input, it's always going to have the same sign. So if I drive 1 volt in here, positive 1 volt, I'll get positive some voltage over there. If I drive this with negative 2.5 millivolts, I'm going to get some negative voltage over here, and I'll be able to amplify it accordingly. So we need to just jump into it. It's not hard, it's not a complicated derivation, but we're going to do it step by step so that you understand. So I want you to recall a few things. I want you to recall that this voltage at this terminal and this voltage at this terminal, I've labeled them V1 and V2, but because of the ideal op amp and the virtual short condition that exists there, V1 is always equal to V2. Now for a real op amp, they're really close within a few millivolts, but for an ideal op amp, we're saying that they're actually equal. And also recall that I sub 1 is equal to I sub 2 is equal to 0. I haven't labeled them here, but I sub 1 is the current flowing into this op amp. I sub 2 is the current flowing into that op amp. But because real ideal op amps have an infinite input resistance, no current can go into there, so we know that there's no current there. So we're just writing this down. Okay. Because all of these things are true, which should come as no surprise to you because we've been talking about it forever, then the following is also true. V2 has got to be equal to this. V2 has got to be equal to VG, whatever that is. And we've done a problem like this very similar several lessons ago. When you have a voltage source here connected through a resistor into the input of an op amp like this, you know that no current is flowing into this op amp. It isn't because this is an open circuit here. So it's almost like you cover it up and it's just open air. This thing, the other side of this resistor is just connected to nothing. It's connected to 100 billion ohms or something crazy like that. So there's no current flowing through it, so whatever the voltage is on this side has got to be the same exact voltage on the other side because there's no voltage drop across that resistor. So if this were, for instance, 1 volt on this side, then it would be 1 volt here. If it were negative 3 volts, it would be negative 3 volts here because there's no current going through that resistor. So what I'm saying is the voltage V2 is the same as the source voltage VG on both sides of that resistor. That's all I'm saying. Okay? And this is because of the fact that I sub 2, the current going into the op amp, is equal to 0. So because this is true, and because of the virtual short, then I also know that V1 must be equal to V2, which must be equal to VG. So all I've done is a lot of complicated looking math, which basically says that since these guys are the same voltage, and because this voltage is the same as this one, you know what the voltage up here is, V1, it's equal to the source voltage. That's the punchline. That's all you need to know. Because of the virtual short and because there's no current in the op amp, if this were 5 volts, then this would be 5 volts, which would also mean this were 5 volts. If this were negative 2 volts, then this is negative 2 volts. This is also negative 2 volts. All of that stuff doesn't require analysis because it comes from the ideal op amp assumptions. So you don't have to, as long as you know what those are, which the virtual short condition between the terminals is always true, and there's no current going in the op amp, then this falls out straight away from that. All right, so that's important because you know that this is now equal to VG. So what this means when you really look at it, if you turn your head sideways then and kind of ignore the bottom of this op amp, ignore the source, ignore this, ignore the triangle even, and you look at this voltage and kind of see that it goes across this resistor, and then you have kind of a tap-off point, we call it V1, and then it goes through this to ground. If you turn your head sideways, this kind of becomes a voltage divider, right? When you look at it. This voltage is kind of across the whole thing because this is tied to the same thing as here. The V0 is across the entire set of resistors. But in the middle, you have a tap-off point. We call it V sub 1. So it becomes a voltage divider like that. And I'm going to show you, I'm trying to decide if it's better to show you here or on the other board. I think I'm going to show you on the other board. So let's just slide right over. Again, turn your head sideways. You'll see this as a voltage divider. I'm going to draw it for you so it's a little bit clearer for you to see. Okay, so this becomes a voltage divider, or you can model it as a voltage divider. And what I mean by that is the following thing. You have this resistance, and then you have another resistance, and they're connected to ground. And this one is called R sub S, and this one's called R sub F. And then here you have plus minus V out. And then here you have a tap off, and this one's called V sub 1. So you need to be able to look at these two things and see that they're the same thing. If you look sideways, the voltage at the far end of the RF is called V0. That goes all the way to ground, which means it connects across both resistors. That's why V0 goes from here all the way to the bottom and across both resistors. The only thing is right in the middle between these two resistors is something we're calling V sub 1, like this, okay? So when you look sideways, you should see that. Now, because it's a voltage divider, the rest of the analysis is kind of incredibly simple. Because then, you know, what's the point of a gain equation? What are you trying to find? You're trying to figure out what the output of the op-amp is as a function of its input. When you know the output as a function of the input, you know the multiplicative thing in there, the multiplicative thing that when you multiply the input times that to give you the output, that's what we call the gain, right? So you need a relation that relates the output to the input, and we'll see how we get there in a second. So what we can do is we can say then the following is true. V sub 1, just looking at this diagram straight as it is going to be equal to this voltage drop, V0, times what? Well, it's a voltage divider. It's this RF over the sum of them, right? Or actually, I have it wrong. It's not going to be times this, it's going to be times this guy. So it'll be RS over RF. You know what, let me write it. It's the same either way, but I'm going to write it as RS plus RF. Make sure you understand that. Basically, you have a voltage from here all the way down. What you're saying is that this tiny little fraction of the voltage, V1, from here to the ground, is equal to the total voltage times the fraction of this resistance divided by the sum of the total. This is a simple voltage divider from basic circuits, right? And that's what it is right there. But we also have another constraint. We know that V1 is equal to VG, and that we wrote a long time ago here. V1, this guy, is equal to the source voltage because of the virtual short condition and everything else we talked about. So basically, even though I wrote it in terms of V1, I'm going to rewrite the whole thing again. It's kind of a waste of ink, but I'm just going to rewrite the whole thing again. We're going to say that V sub G is equal to V0 times RS over RS plus RF. Now look at what we have. The input voltage, the output voltage, these are kind of variables. You can change one and the other one changes. But these resistors are functions of the circuit, right? They're just resistors. You can change them and change everything else. So what we want is we want the output of the circuit as a function of the input. Here we have the input as a function of the output. So we're going to rearrange and solve for V0. So basically, if we flip this around again, what we're going to get is V0 is going to be equal to Vg. When we divide by this mega fraction on the other side, it's going to flip that fraction over. So you're going to get Rs plus Rf over Rs. Let me double check I'm right. So now we have the output of this circuit as a function of the input. This is the multiplicative asset that basically changes the input multiplied by this to give us the output. So this quantity right here is what we call the gain of this amplifier, okay? That's the bottom line, okay? Now, there's a couple of different ways to write this, but this is the simplest way to write it. You have the input times the gain gives you the output. Now, notice this gain is very different than the gain for the inverting configuration. The inverting configuration was simply a negative sign in front, feedback resistance divided by source resistance. Very simple fraction with a negative sign in front. First of all, I want you to notice there's no negative sign here. All of these resistors are positive numbers. Resistors can't be negative, right? Not in circuits, and not in basic circuits anyway. So since all of these are positive numbers, there's no negative sign in front. That means that the output signal is always going to be the same sign as the input signal. That's the proof of what I've been telling you. This is what we call the non-inverting configuration. It does not invert the signal because there's no negative signs here, whereas the gain equation for the other one actually had a negative sign there. Now what we're going to do is rewrite this a little bit further. This is fine to use, but I want to, I want to make it a little bit clearer. So make sure I have this correct. What we can do is we can rewrite this. We can say, actually I'm going to change colors. We can take this relation and make it a slightly simpler. We could say V0 is equal to Vg. And on the inside, notice what we have, a big fraction, right, divided by this. So we could rewrite that as Rs over Rs plus RF over RS. Make sure to understand this. If you add these fractions together, you have a common denominator and you'll add the numerators. All you're doing is splitting the fraction up, but RS over RS, this is just a fraction equal to 1. So we can say that V naught is equal to VG 1 plus RF RS. This is a very common way that you can write it. Either of these is totally fine, but you could also say that this is the gain. All right, this is the gain. So let me go ahead and just on the next board, let me go ahead and write the gain down again, and then we're going to talk about some interesting facts that come about because of this. So all I'm going to do is rewrite these two equations exactly as they sit. Or I shouldn't say I'm going to rewrite them exactly as they sit. This is the output as a function of the input. I'm going to write the gains down on the next board so we have a nice clean board to talk about, and then we'll draw some conclusions, and then we'll be done with this lesson. Basically, here's what we call the gain of the non-inverting op-amp. Right? There's two ways to write it. Depending on your book, you'll see it two different ways. The gain can be written as 1 plus the feedback resistance over the source resistance. Or the gain can be written as RS plus RF over RS. So this by far is the most important thing to write down. And it's exactly the same thing here. We have RS plus RF over RS, 1 plus this fraction. All I've done is take those out and write them down. Okay, so this is the most important thing here. And those of you that look carefully at this top version of it, this is why it's very nice to write it like this. What do you see from this? These resistors they always have to be positive. I mean, whether or not they're big or small, they're always going to be positive, and so this fraction is always going to be something bigger than 1, right? It may be really tiny, 0.0001, whatever, or it's not going to be, I shouldn't say bigger than 1. What I'm saying is going to be a positive number, something. It's going to be a positive number. When you add this to the number 1, what you're going to find is the gain of this configuration is always greater than 1, always, and that's really important. So I'm going to write that down. The gain is always greater than 1. There are no resistors that you can hook up into this configuration to get a gain less than 1. Even if I put 1 on the top and 100,000 ohms on the bottom, I'm still going to have a positive number. It'll be small, but it'll be positive, and I'll be adding the number 1 to it, so the gain will be 1.00000001. It'll be slightly bigger than 1. That means that, and this is incredibly important, you always have a positive gain greater than 1 when you build this amplifier configuration like this. So if you think back to the inverting amplifier, I know it's drawn a little weird, but when the gain was this divided by this with the negative sign, you could choose those resistors, so sometimes you had a gain bigger than 1, sometimes you had a gain less than 1. That means you take your signal and you make it smaller, right? If your gain is less than 1, you're multiplying the input signal by a fraction, negative sign, but by a fraction, to make the output smaller. In the inverting configuration, you had that flexibility to make a gain smaller than 1 to actually make your output signal smaller. Here, you don't have that flexibility. You cannot create a gain smaller than 1. So the best you can do, if you choose these resistors to be equal to one another, is you have a gain, well, even if you choose them where one is very big and one is very small, you're always going to have the closest you can get to 1 is going to be super, super close to 1, 1.000 something. And then all the other gains are going to be higher than that. So basically, don't use this configuration if you actually want to attenuate your signal. That's what we call it when you make the signal smaller. We attenuate it, we make it smaller. If you want to make the gain bigger and power a loudspeaker or something, great. The gain's always going to be bigger than 1, but don't ever try to make the signal smaller than the input signal because you can't do it. The minimum value is going to be a gain equal to 1, which means it'll be the same size as the amplitude as the input. Also, these resistors in the gain equation, RF and RS, these are these resistors. These are the resistors that aren't even connected to your source. This we called RG, remember? And believe it or not, RG didn't actually come out in the gain equation at all. RG, the input resistance that comes out of the source that you're driving, is irrelevant to the gain of this amplifier, right? The amplifier is only dependent on the other guys, and we've gone through all the math, you know, as to why in the past, but basically these resistors govern the gain, okay? Just as before, it's just you can't make a gain less than 1. Okay, so the final thing I want to write down that you'll probably see in a book, and I just want to explain it to you, for linear operation. Remember, what does linear operation mean? It means that the output of the amplifier, V out, has to be between these power supply signals that we have. So something you're going to see in your book probably at some point is going to be an equation that looks like this. It's not terribly useful, but you'll see it, so I'm going to explain it to you. You'll see something like this. 1 plus RF over RS, this is the gain, has got to be less than the absolute value of VCC over VG. A lot of students look at this and say, what does this mean for linear operation? What does this mean? All it means is that the gain has to be smaller than this fraction, right? Because if you make the gain too big, then you're going to blow out and saturate the output. It's going to be too big. So another way to look at this to kind of make it more, have it make a little more sense, multiply both sides by VG. And what you'll see, in other words, this is what I like to write in other words. If you multiply both sides by VG, you have 1 plus RF over RS times VG has got to be less than VCC. And I'm taking away the absolute value signs and assuming positive values to make it easier to understand. Basically, if you take an input signal, this is the input you're driving the thing, that you're amplifying, and you multiply by the gain, then this value, after you multiply by the gain times the input, has got to be less than VCC. It means the output, which is what this is. This is the output, right? The gain times the input's got to be the output. It must be less than VCC. It's the constraint on linearity, because by definition, linear means the output has to be less than VCC. If you're talking about positives, I mean, of course you have the negative side too. That's why we have the absolute value here. But basically, if you take the input as a positive value times this positive gain, it better be less than or equal to, I guess, probably less than, safer, than VCC. Another way to write that is this. Basically, the gain has to be less than this fraction, and that just comes straight from multiplication. It's a little easier to start looking at this one and back up and realize that this must be true. So basically, if you know what VCC is, you know what the input signal is, then you can calculate the maximum gain that you can allow this thing to get to have in order to not saturate. That's basically it for this lesson. Basically what we talked about, just a quick recap, is we had this idea of an inverting amplifier. That's what we were studying all the time. We take the input signal and it inverts to make an output signal. How could you then create an output signal that was non-inverted? Well, you could sandwich these guys together and put two amplifier stages together. So you invert it here and you invert it again here. But then you have two amplifiers. It makes things complicated. So we say, without proof, that this is what we call a non-inverting amplifier configuration. And basically, to prove that it's true, that it is non-inverting, we realize that this voltage, because of the constraints on the op amp, must be the same as V2, which then must be the same as this at this point right here. So then we go and look and say, well, this looks an awful lot like a voltage divider. So the output voltage, whatever it is, falls across those resistors, and we write an equation showing that. But since we know that V1 is equal to the source voltage, we can replace it, and now we have an equation that relates the output to the input voltage. So we flip it around and get the output voltage as a function of the input voltage. This is what we then call the gain. So we then write the gain of this configuration down in two ways. You might see it different ways in your books, but they give you the exact same thing. But then you have to realize that you always have a gain greater than 1, right? So you do have the simplicity of a non-inverting op amp, but you can't attenuate your signal. It always is going to be 1 or greater there. And then we had some discussion about the linearity there. So make sure you understand this. We're going to do some problems in the next few lessons so that you will understand how to use these concepts. And so once you understand these ideas, follow me on to the next section. We'll do it right now.